So to summarize, to get the moment of inertia for a given shape, let's say about the x-axis at the centroid of the shape, we get that I0, 0 standing for about the centroid, equals integral y squared dA, and that's I0x. And I0y, the integral about the y-axis, is x squared dA when x is measured from the centroid. The question I have for you is, what if I want to know the moment of inertia about an axis like this that's not the centroid? What is I now? It will be bigger, right? So if you think about it, it's easier to spin something about its centroid than it is to spin something around another edge. So it's easier to spin that rectangle about its middle than to spin it about its left edge. But exactly how do we calculate this new moment of inertia about a new coordinate system, not the centroid? We do that using something called the parallel axis theorem. It will relate the moment of inertia about the centroid axis to the moment of inertia about another axis that's parallel to the first axis. And this high performance equation is simply I about another axis is just I about the centroidal axis plus AD squared. All you do is add AD squared, where D is the distance from the new axis to the centroid axis. You take moment of inertia about the centroid axis, you calculate the area, and the moment of inertia about here is going to be I0 plus AD squared. That's why I knew that the moment of inertia about the centroidal axis is the minimum, because anywhere else you're adding AD squared. We'll illustrate the moment of inertia using 3 examples. We'll do a rectangle about its centroid, and then the rectangle about the bottom, which is not the centroid, and then we'll do the moment of inertia of a circle. This is one you should really memorize. The moment of inertia of a rectangle about an axis, if that's B parallel to the axis, and this is H, the moment of inertia is 1/12 base times height cubed. And by the way, moment of inertia always has units of length to the 4th. So here we've picked our coordinate system at the centroid of the rectangle, which is right in the middle. And all we're going to do is that I equals integral, I about x will be integral y squared dA, and that's I0x. Okay, we have y going from minus h over 2 to h over 2. dA is the area of that little differential area, which will be b dy. So we need I equals the integral from minus h over 2 to h over 2 y squared b dy, and that's simply b 1/3 y cubed from minus h over 2 to h over 2, which is just b times 1/3 h over 2 cubed minus h over 2 cubed, and that would be b 1/3 h cubed over 8 minus h cubed over 8, which is b times 1/3, and h cubed over 8 plus h cubed over 8 is h cubed over 4, which equals 1/12 base times height cubed. Next, we want to get x about the bottom. One way to do this is to do the exact same thing, but now put your coordinate system here at the bottom. And we could do this, and it would take a couple steps to do it like this. We'd have to take the integral from 0 to h, and we would have to do this all over. And that would come out to be integral 0 to h y squared b dy, and that would equal b times 1/3 y cubed from 0 to h, which is 1/3 b h cubed. That wasn't too bad, but that took 2 steps. We had to set it up, do the integral, plug it in. We could do it in one step, in one less step. So that would be like getting a birdie in golf. It would be one step less. But anyway, to do this without doing an integral, you just get I about the bottom equals I about the centroid, which we're calling I0, plus AD squared. So that equals 1/12 base times height cubed, right? Which is I about the centroid. We just did that. Plus the area, b times h, times the distance squared. And so the distance from the centroid to the bottom, this distance here, is h over 2. So that will be times h over 2 squared. So this is 1/12 bh cubed plus, let's see, 1/4 bh cubed, which is bh cubed times 1/12 plus 3/12 equals 4/12 bh cubed, which is 1/3 bh cubed. Now that I've done it both ways, maybe the first one was easier now that I think about it. Okay, let's see if we can derive the moment of inertia for a circle, which is pi r to the 4th over 4. Again, we're just going to do I0 about the x-axis is integral y squared dA, and dA is just 2x dy. We're going to need to change that x into a y, but we know that x squared plus y squared equals a squared, or that x equals the square root of a squared minus y squared. Okay, putting that all in, we get I equals integral y squared dA equals integral, and we're going to do this integral from minus a to a, y squared dA, which was 2x, which was 2 square root a squared minus y squared dy. And so we have I equals the integral of 2 minus a to a, y squared square root a squared minus y squared dy. Okay, so we're going to have to do this integral. I'm going to cheat, and I'm just going to put that into Wolfram alpha and see what I get. So I'm sorry to report that Wolfram alpha, which used to be aristocratic upper class, is now bourgeoisie or middle class. It's been influenced by private property interests, and is no longer free for difficult integrals like this. So I'm going to actually have to do this by myself. So what we have, if you think about it, just a minute. If we draw the triangle to the point on the circle, where this is the radius A, this is Y, this is X, and that's theta. Y is a sine theta, and X is a cos theta. But X, by Pythagorean's theorem, is also square root of a squared minus y squared, right? Because a squared plus y squared equals x squared plus y squared equals a squared. Solve for x, you get that. So what we get is that square root of a squared minus y squared is a cos theta, and we have y equals a sine theta, and so y squared equals a squared sine squared theta. And we will also get that dy equals a cos theta d theta. Okay, so we're now ready to do the integral. I equals 2 integral minus a to a y squared square root a squared minus y squared dy. And so when y equals minus a, sine theta is minus pi over 2, so equals 2 minus pi over 2 to pi over 2. Okay. Y squared is a squared sine squared theta. Square root of a squared minus y squared, we said, was a cos theta, and dy was a cos theta d theta. And so this will all equal 2a to the fourth integral minus pi over 2 to pi over 2 sine squared theta cos squared theta d theta, which we can do by integrating by parts, but I'm hoping that at least this integral will be free on Wolfram alpha. And yes, you could get this integral for free on Wolfram alpha, and it equals pi over 8. So 2 a to the fourth times pi over 8, which is pi a to the fourth over 4, which is the desired result.